Okay, hi everyone. It's my pleasure to be here. So I'm Ligeng Zhu, so currently research assistant from MIT Han Lab. So today I'm going to present our I'm going to present our recent work, AutoML for efficient neural architecture design. So deep learning has made a great process in recent years. And along with the process, so the data side and the computation side, as well as the model depth has grown rapidly. So for last century, a simple net of only 5 layers network, now it has become to 152 layers. Even this kind of network has outperformed human on certain benchmarks and has very impressive applications in various domains. It's become really hard for humans to deploy it as well as design it. Consider if every layer may have, for example, 10 possible combinations, and 10 to the times of 155 is not some space can be explored by human experts. Due to meantime, so such a network makes specializations very hard. So previously, people used a simple single efficient neural network for all platforms and all data size, because designing an efficient neural network takes a lot of engineer efforts and a lot of trial and errors. But we noticed that actually different hardwares has different preference. So for example, CPU has higher frequency, but not good at parallelization, and the GPU is very good at parallelizations, but has lower clock speed. So such a difference, well, it's not very well studied in the current CNN design domain. So currently, we think that so machine learning wants to a generalization. So one model, once designed, can be deployed everywhere, every devices. But actually, hardware requires specializations. So needs things especially design and fit into some properties of its own hardware. So a generalized model to handle specialized hardware is actually not ideal. So you can see we have many different platforms. So the FPGA, the GPU, CPU, SoC, and many, etc. And we also have kind of different data sets like the CFAR, ImageNet, places, and more. So if you, for each scenario and each hardware, you do a specialization design, then it's not that tolerable. You need this kind of combinations. You don't have the human bandwidth to explore. So what we want is we want to move the manual design from the manual design to automatic design. Let the neural network designed by some machine learning algorithms instead of a group of engineers, many trial and errors. Yeah. So this is our proposed pipeline. So previously, we only designed one good network, like the ResNet, the Inception, the DenseNet, or the MobileNet, for various platforms. And now we want to have algorithms that automatically designs for one platform and one data set and one scenario. So such specializations can not only reduce the effort for designing a network, but also allows our automatically designed network to run much faster. And another benefit of this automation is it allows non-expert to benefit the growing of the machine learning algorithms. So currently, the CNN network is kind of like a privilege for machine learning researchers and big companies, since many companies does not have the bandwidth to develop a team to develop their own network. But with such design automations, you just need to press the button, and then you can do a specialization for your own user case. So this allows non-expert to efficiently design your network and runs faster on their own hardware. Okay, here is the background, and now we are going to the method part. So conventional NAS, so neural architecture search has been explored for a while. But as I said before, so people want automated design because they think human design is time-consuming and expensive. Conventional NAS so made some progress on the performance, but still very expensive. Like first, for example, NASnet proposed by Google, it requires 48,000 GPU hours, which means if you only have one GPU, it requires to run 1 year. Yeah. So actually, it may be even more expensive than you hire a group of researchers to design a network for you. And there are some improvements, like one famous one is DARS. So DARS greatly reduces the GPU hours, but however, it requires a much larger memories. So GPU memory, unlike the CPU one, you may have like 100 of gigabytes or even 1 terabyte. So currently, even the most fancy GPUs can only have 32 memory GPU, like the V100. However, the DARS, if you want to do a human-level fully design, so it will require 100 gigabytes of memory, which exceeds the limits of most modern GPUs. And because of the expensive on GPU hours or GPU memory, so most NAS work previously are based on the proxy. So proxy has several common ways. So one common way is, okay, so we may not search on your final data set because your final data set may be very large, like ImageNet. It has millions of images. So instead, they do not search on millions of images. They just search maybe on a small data set like CIFAR 10, so which only consists of 50,000 images. So it can greatly accelerate the process. Or maybe they do not search the whole architecture. They just search a part of the architecture and build a deeper network by stacking the same layers. And another way is, okay, maybe we do not need to train until converge, because if you want to train a deep neural network to converge, it usually takes like hundreds of epochs, and you can maybe train it on 5 or 10 epochs and to see which one is the best. Okay, so such proxies will indeed give some improvements on the efficiency, but it does not really help or it introduces some new problems. So some limitations of proxy is about the suboptimal. So for example, if you search on a small data set and then transfer to a large one, which means many properties of the large data set is not considered. So you are optimizing for the small data set instead of the large one, and such gap may reduce the final performance. And when you search for some small architectures and then repeating it, actually your architecture search loses diversity. Your architectures will just a series of repeating blocks, not like specialize each layer for your target scenario. And there's a few epochs also brings some new problem, like, for example, when you do the training settings, so models with fewer parameters usually learns larger if you do not consider weight decay. So all these kind of suboptimals makes such a proxy is not ideal, but which is necessary because otherwise it's too costly. And also, such a proxy means you cannot direct optimize for your target hardware. So currently, most previous works, they only consider like the accuracy as the only evaluation metric for their search. Yeah. So our work aimed to solve these problems is called Proxyless-NAS. So what we want is, okay, conventionally NAS relies on the proxy task, and we want to remove the proxy. That's why we call it proxyless. And if we remove the proxies, so the cost grows rapidly. So we want to make our work efficient. So our goal is directly, without proxy, learn architecture on the target task and the target hardware, while allows all blockings to have different structures and in a very efficient manner. Yeah. So in general, we achieve it by 2 ways. So first is reducing the cost of NAS to the regular level of our training. So which means now you do a search, is the cost of search efficient model is as cheap as a normal network. And the second one is cooperating hardware feedbacks into our search process. So the search architecture can be customized to your target hardware. Okay. So yeah, so the first part is to make NAS more efficient. So unlike many big name industries, which has a lot of engineers, a lot of high-end clusters, and a lot of GPU parts, yeah, we do not have such a power, yeah. So we only have to think about the smart algorithms, yeah. But luckily, we find an efficient algorithm. So our our methods inspired from the combination of model compression and neural architecture search. So we save the GPU hours by model compression, yeah, and we save the GPU memories by binarization. And here is the details of our algorithm. So first, we reformulate the NAS program, NAS algorithm. So conventionally, so say do the NAS search is based on the reinforcement learning. Every time they sample a network, yeah, and train from scratch, gets feedback into the reinforced agent and performs the next step, yeah. And in our work, we reformulate into a pruning, path level pruning problem. So which means first, like shown in this figure, we have a large network which consists of many possible paths. So at the searching stage, so each path has its own architectural parameters. So at each searching stage, we train both the weights and also its architectural parameters. Yeah. And after we finish the searching stage, only the path with highest architectural parameters will be preserved. So after searching, we can prove all other paths, so we can get a slim network. So by doing so, we simplify NAS to a single training process on an over-parameterized network. So no meta controls, no reinforce, no multiple samplings. So we only need to train one joint network. So this makes our save the GPU's hours by 200 times. And next, we are going to do, and notice here is like if we do it in a naive way, so memory access, so memory footprint is actually grows as linearly as your candidate size, which means if you have 10 candidates, you may have like 10 times larger memory. If you have 100 candidates, so you will have 100 times memory. So which limits the total search space is not what we want. So next, we are going to save the GPU memory. So to save the GPU memory, so we binarize the architecture parameters and allow only one path activations to be stored in the GPU during the forward and backward trainings. So by doing so, we reduce the memory footprint from ON to O1, and all architectural parameters is not it's not updated by the gradient descent. We can do it in our reinforcement learning, and then we can reduce the memory footprint to a constant factor, so we can perform search on a large search space. And then by doing so, we solve both CPU hours, GPU hours, and GPU memory issues. And the next we are going to do is to include a hardware feedback into our consideration. So to perform the hardware-aware neural architecture search, we need to get the latencies from the target platform. So in our experiment, we focus on CPU, GPU, and the mobile CPU. But if we directly measure on the target devices, it's very slow. So for example, inference neural network is usually 300 milliseconds, and to get a precise number, you need to do like at least 20 times run to get an average. So which means to get one latency, you need like 6 seconds. So which will significantly slow your searching process. So to avoid it, we noticed one interesting is because the neural network actually, so every layer's computations, memory access is very heavy. And we can take computation of every layer or every block as an independent process, because every time it will flush all the caches. So the computations of previous layer is not that important to this layer. Yeah. So by doing so, we can take every computings of every layer as an independent process. Thus, we can build a low latency lookup table to quickly estimate the latency. And as you can see on the right, so y-axis is real latency, and the x-axis is our estimated latency using the latency lookup table. So the two actually matches quite well, which means our latency lookup table is a good estimations. So we use latency lookup table as our economical way, as an alternative, as we said. So our research team do not have many fancy hardwares, and our resources quite limited. So we have to do everything in an efficient manner. So, and doing so, we can then optimize the neural architecture by using the gradient or reinforced in both ways. And here is a search history of our architectures. And you can see the first is, it's not showing here. So first one is the searching process of mobile model, yeah, specialized for the mobile CPU. And the second is specialized for the desktop CPU. And the third one is specialized for the mobile desktop GPU. So for the mobile phone, we'll use the Pixel 1, and for the CPU is Xeon, and for GPU, we'll use V100. And here's the search animation. Is it enable? Okay, yeah. And let me explain a little bit. So the blue one means the kernel is 3 by 3, and the yellow one is kernel 5 by 5, and the red one is kernel 7 by 7. And the width respect to the expansion ratio, so how many channels inside each one. So you can see during the search process, so actually the layers, especially for the GPU one, it is become more shallow, and more shallow, because GPU has more parallelism. So it prefers a shallow network, but with large kernels, so it can better parallelize. And for the mobile CPU and the desktop CPU, they both choose slim but deep neural architecture because they have less parallelism. Yeah. And one thing we have noticed very interesting is also the kernel choices, kernel size choices. So if in a long time people believe the 3 by 3 kernels is better because 3 by 3 kernels, 3 by 3 kernels have the same receptive field but less flops than 5 by 5 kernels. But we noticed that actually in many platforms, like especially the mobile CPU and the desktop CPU, even it has less flops, but the deeper network requires you to store more activations. So it's actually slower in the real inference. So choosing a large kernel and reduces the network depth sometimes makes your network even more efficient. And here is our accuracies on the CIFAR-10 dataset. So in the first section, so the DenseNet, Primate, Shake, and the PrimateNet plus SD. So these models are designed by human experts, and you can see they achieve errors above 2.31, yeah. And in the second section is conventional NAS algorithms. They try to search on it, and you can see they achieve better performance than human design. And the last one, yeah, Proxyless-R and Proxyless-G is our proposed method. R stands for the search by reinforce, and the G stands for the by gradient. And you can see our search algorithms is much faster than is much better than previous methods. And more notably, so even compared with the conventional NASnet, for example, the mobile-net, so the last one is the second section. So it achieves a similar accuracy, but it uses 7 times more parameters than our network, yeah, which shows the power and effectiveness of our algorithms. And next is our results on the ImageNet dataset, mobile platform. So we choose the MobileNet V2, which is current industry standard and our baseline to compare with. You can see in different latency settings, our models consistently outperform MobileNet V2. And to achieve this accuracy level around 74.7 or 0.6, yeah. Our network is 1.8 times faster than the MobileNet V2, yeah. So, all right, and here is more robust comparisons of mobile efficient thing on the mobile. So for the mobile net V1 and V2, yeah, they have the top one accuracy is above 70, and with latency is 110 and 75 respectively. And for the last part, so they improve the accuracy by a greater margin. But however, the latency is also grows because they do not consider hardware feedback during the search. Yeah. And also notice the last column of the NAS network. It requires ridiculous GPU hours, yeah, which is unaffordable for research team to reproduce and follow. So this work are all done by Google. And our work, yeah, you can see, okay, so we have various settings. And in all these settings, we achieve our accuracy is as good, and in some settings even better than conventional NAS. And as our work consider hardware feedback during the searching process, so our network is also runs much faster as the original mobile V2. And most notably, so our search cost is just 200 GPU hours. It's at the same level of training a neural network, which makes our work reproducible and affordable by other teams. And here's our results on the GPU platform. So we measure human design models, previous NAS works, and our models on the V100 GPU. Yeah. So you can see on this one. So our models has the best accuracies, while runs the fastest on the V100 GPU. And even compared with Google recent MNAS network, in their framework, they also take the hardware feedback, considers the hardware feedback during the search. Our work is still 20% faster than CR's one, where it has 1.1 top one accuracy improvement. So yeah, from here, so what we did is, first we want to efficiently search a model. So previously training a network, so y-axis is at the log level. So previously training a network is usually around 100 GPU hours, yeah. So, but if you want to automate the process, use the conventional approach, it requires more than 10,000 GPU hours, yeah, which is unaffordable for most teams. And we reduce it by 200 times to the regular level of normal training, yeah. And also save the GPU hours. And also we search and efficient models, yeah. So you can see on the top is the conventional NAS. So y-axis is the accuracy and the axis is the flops. So even they have better accuracy. Sorry, I made a mistake. So the y-axis is the latency. So you can see even pre-conventional NAS, they take the flops as an evaluation metric. So they have very small flops, but actually they are not hardware friendly. On the hardware, it's actually very slow. And our network, so even our flops are very similar, we run much faster on the desired hardware. Yeah. And one more interesting we have got from this work is some inspirations from the architecture design. So 2 points I have mentioned before is the large kernel and also the depth. So, right. So we always think large kernels is not good, yeah, because it has better flops. But a large kernel with shallow network actually allows your network to run much faster, yeah, on various platforms. You can see in conventional work, they only use 3x3, but in our neural architecture search, even for the slowest mobile CPU, they choose many large kernels, yeah, try to improve the speed, yeah. And also in the GPU platform, such a shallow and dense design is first to be discussed, because previously design a network is too expensive. So people want to design a network can be run everywhere. They do not consider the property and they do not specialize for each hardware. So this point has been ignored for a long time, and we hope we can raise this awareness for people. And as expected, so if you search for a certain platform, it will give you low-hanging fruit. improvement on this platform. You can see model searched for GPU is runs fastest on the GPU, searched for CPU is run fastest on CPU, and the search for mobile is fastest on the mobile. And you can see their performance are actually very close. So which means give us a very interesting feedback. So sometimes if you're training a good network on the GPU, yeah, and then now you want to deploy it to the mobile, and you think it's not enough, fast enough. Actually, you do not need to to change your inference code or try to compress it to make it faster. You just need to specialize it, and you can get us a free improvement. And based on this work, we also made some achievements on the design automation. Yeah. So recently, we have used the Proxyless-NAS to win the first place in the Visual Wake Up Word Challenge in CVPR. So this challenge is aimed to so it's kind of keyword wake up. So just like use Siri, use Hey Siri, and it should respond as fast as possible. So challenge part is the model size is very limited, and the peak memory usage is also limited, and the flops is also limited. So conventionally, people may manually tune our settings or try search our settings for this one. But in our work, we just feed in these hardware feedbacks, and it can automatically search a feasible solution for us. And not surprisingly, our automatic search one is much better than human-tuned. And we also won the third place in the classification track of the low-power computation. So it's kind of try to do image classifications within 30 milliseconds latency on Pixel 2 phones. And again, we just put the hardware feedback into it, and it automatically search a feasible solution for us. Yeah. So this shows the power of design automations. So design automation not only allows non-experts to enjoy the benefit of deep learning, but also in many cases it can outperform human experts. So yeah, as this event is inside the Linux Foundation, and our work has based on many great open source tools. We also love open source. So our code are now released on the GitHub with pre-trained weights and the searching codes. Yeah, you're welcome to start it. Yeah. Any question here?
So this is intended for convolutional networks?
Yes.
Does it work for non-convolutional networks?
Do you mean like some language model, LSTM or ARMS?
Yeah, or just straight?
Yes, so we are currently working on it. Yeah, so, but this way is, so problem is we are not that familiar with NLP task, so this project is still ongoing, but on some simple task, we have shown that design automation is also practical.
What's the language?
Sorry, what?
What language is the API? Sorry. What language is the API?
You mean what language model we are using?
Yeah.
So currently we are trying to start with sequence-to-sequence translation. Yeah. So we are trying to let the machine learning algorithm to automatically search a good sequence-to-sequence model. Yeah. But this is still ongoing.
Thank you.
Any more questions? Okay, so I'm going on. So from then on, so we have talked about how to use machine learning to search and efficient models. But in your search, are you memory bounded or CPU bounded? You mean my search process is CPU bounded or memory bounded? I think it will be GPU bounded. Yeah, if we have more computational sources. Sorry, you mean the search the model or searching process?
The process.
The process is, I think it's GPU bounded.
Not memory?
Not memory so far, yeah.
Okay.
Okay, any more questions? Okay, so, right, we just talked a lot about how to use machine learning to search and efficient models. But for a deployment, so just searching a model is not enough. So usually after you design a good model, you also need to compress it. and then you may need to quantize it to make it actually runs faster on your hardware. And yeah, so we also do these 3 steps of works. So we first use Proxyless-NAS to search an efficient neural network. Then we use the AMC, which stands for the AutoML for model compression. And also we use the HARQ, hardware-aware quantization, to fully automate this process. So with these techniques, you can just press one button and let the machine learning algorithms to do every step for you. And all this work now has been accepted to conference and now open sourced. And next, I'm going to introduce about the AMC and HARQ. Okay. Yeah. So, right. After you have a model, you always need to do pruning, and the prunings you have different levels. So for the fine-grained level, yeah, it can achieve the best sparsities, but it usually needs specialized hardware to support it to run faster. So, but for the best one, which is the field level pruning, so which is most hardware friendly, but also the sparsity is somehow limited. So conventionally, you have a customer, you have a model, and you can let your engineer teams to work for it. But if you have more models or more tasks, then your work just bounded by the human bandwidth. So our goal is to use AutoML to automate this process and allows this to achieve human level and even outperform it. So the process here is based on the reinforcement learning. So it's kind of like a human process, but just the human agent is replaced by the RL agent. So we have a network, and we set the pruning levels, and for each time step, we sample an actions, which is how to prune the network, and then we quickly calibrate it and get the accuracy. So by doing so, we can get desired flops and accuracy. We can feed it into agent and get an update. And you can see on the pruning agent, so it's actually find some interesting patterns. So for this one is, okay, let me explain a little bit. So in this one, it shows the magnitude of how many ways and the total, how many non-zero ways and total ways are pruned in the sections. So you can see our agent automatically learns that 1 by 1 conv it has less redundancy and should be less pruned. And the 3 by 3 convolutions has the most redundancy. So you can see many peaks in this design. So which means these peaks stand for the 3 by 3 convolutional kernels. Yeah. And right, and you can see our AMC. So here's plot of x-axis, which means the flops, and the y-axis remains to the accuracy. So conventionally, if you prune by human expert, which is a red dot, only can achieve some several limited trials, and the AMC achieves much higher accuracy and flops ratio than the human trial. And you can see also we can use the final inference latency as our target, as our reward. So by doing so, our work will run much faster than previous human designs. So here is our detailed numbers. So for the MobileNet V1, 1.0 with settings, so it can achieve 7.6 accuracy, while runs 120 milliseconds on the Samsung. And we can prune it by 50% of the flops, and it reduces the latency by a great margin, while the accuracy is almost no changed. We can also prune it by 50% of the inference time, and you can see the accuracy, so is literally dropped, but still acceptable. So it really runs 2 times faster than the original one. So compared to manually scheduled with setting, which has a similar latency, the accuracy is dropped by a large margin, and our method is significantly outperforms the manual tuning. And here's the comparisons of the previous one. with previous human experts, which is Professor Hans thesis. So you can see previous expert tries very hardly to prune the network. And for each one, it chooses a different threshold and has to be very careful, otherwise the accuracy will drop. So here is the pruning ratios of each convolution layer. And you can see MC find a better scheduling and how many should be pruned in every block. And actually, the pruning ratio is 3.4 times, is improved from 3.4, which is previous status of the art from human expert, to 5 times compression ratio. Yeah, and right, so with this automated process, we not only make this process much simpler, but also better than previous human expert. And the next one is about the hardware-aware quantization. Yeah, so hardware-aware quantization has many useful cases, because currently people notice that so neural network is very robust. You do not always need a single float precision to handle it. So you can use multiple precisions or maybe mixed precisions. But this brings a challenge to design space. So for example, you have n layers in, and you have, so weight can be 1 to 8 bit, and also the activation can be 1 to 8 bit. So the total design space, it can be 64 to the times of n. So this cannot be explored by humans, so we need AutoML to do this task. And this task is also designed by reinforcement learning. And the key point here is we use a special metric to preserve the accuracy. So when we do the reinforcement learning, we are using designed reward functions. And the reward from the latency is the latency quantization minus the latency from the original. We call the improvement and the difference between quantized model and the original model. And for the accuracy one, is the accuracy from quantized version and the original version. To preserve the accuracy, we set the relative weight of the quantized accuracy reward very high to ensure we do not get a performance drop during the quantizations. And as you can see, these results are from different FPGA board. Yeah, because currently no public hardware or framework really supports mixed precision. And you can see we also observe similar trends in the Proxyless-NAS, which means you quantize for a certain hardware and it runs fastest on this hardware. And here is a comparison of previous work. So the blue dot is from the fixed 8-bit quantization from previous state-of-the-art results. And the yellow dot is our results on the flex-bit quantizations. So the y-axis is latency, and the x-axis is latency, and y-axis is top-line accuracy. In both settings, we get the better latency and accuracy ratios. Okay, and yeah, so from this, we do the whole process, and we make this fully automatic, and right. Thank you.